Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate and trust and confidence in science and engineering subjects. Today in our subject electronic devices and circuits, we'll understand energy band theory and will explain classification of material as conductor, semiconductor and insulator as per energy band theory, and we'll explain how the presence of forbidden gap between valence band and conduction band decide the conductivity property of material. So let's start classification of material as per energy band theory. The structure of any pure metal is described as systematic regular alignment of positive ions. This positive ion is basically a combination of nucleus of metal atom and inner orbital electron attached to that nucleus, and these positive ions are surrounded by delocalized outer orbital free electrons as illustrated here. Now these outer orbital free electrons of metal are free to move within the entire volume of metal like a gas molecule in a chamber. So we say electron behave like a gas in metal specimen. Now due to thermal energy, these free electron moves with very high thermal velocity, and during their movement they get collided with other such thermal moving electron, positive ion or impurities, and in those collisions they change their directions, and this motion of thermal moving electron is perfect random, and in the end the free electron come back to the same position. Different free electrons possess different characteristic of thermal random motion, but in all those thermal random motion there is no net charge transfer of electron position or charge by such thermal motion, but such free electrons by such thermal movement can transfer heat by conduction in metal. If one end of metal is heated, then that other end of lower temperature may get heat from high temperature end by such thermal motion of electrons. When external potential is applied across conductor, that potential establish an internal electric field, and due to that electric field, this thermal random motion of free electrons got modified, and all free electrons will experience a force and acceleration due to internal electric field in conductor in the direction opposite to the direction of electric field. But due to the collision among thermal random moving electrons, the velocity of these free electrons in the opposite direction of electric field will not increase with time, but this movement of black directed random thermal motion get modified as red directed new movement, and a free electron will forcefully drift in the opposite direction of electric field with a constant average velocity. Different free electrons possess different type of random thermal motion, but the modified motion as shown by red lines indicate the same forceful drift motion of free electrons, and all free electrons will drift with the same velocity in the same direction opposite to the direction of electric field when we apply electric field by application of voltage across conductor, and this drift velocity of free electrons is directly proportional to applied electric field, and this proportionality constant is known as mobility of electron in metal denoted by mu here. So drift velocity become equal to mu times applied electric field intensity. So we can say when external potential is applied across metallic conductor, it establishes an electric field inside the metallic conductor from high potential positive end of battery connection to low potential as indicated by this red arrow, and all free electron will drift with the same average velocity in the same direction, and that direction is opposite to electric field by the action of this electric field, as this black directed random thermal drift motion which won't produce any shift in electron position or charge transfer get modified as red directed curve, and all free electrons will drift in the opposite direction of electric field as shown here, and this drift velocity is directly proportional to applied electric field, and proportionality constant is known as mobility, and the mobility of free drift moving electron depends upon the average time between collision called as relaxation time. If metal got a higher purity and refined structure, so that During drift motion of these free electrons, less number of collisions will take place and there exists a higher value of relaxation time than mobility of that material having less collision and high average time of collision will be high and that produce higher amount of drift velocity, so more amount of charge will transfer that indicate higher value of conductivity. So we can say this mobility depends upon average time taken by free electron between two successive collision, and this time between collision relaxation time depend upon nature of material, its purity level and mechanical workmanship. A pure annealed metal will have higher amount of relaxation time or mobility. Due to drift motion of free electrons by the application of potential, charge transfer takes place and that result in current circulation, and current per unit cross section area of conductor is known as current density, and current density in a conductor is directly proportional to applied electric field, or electric field is equivalent to potential applied across per unit length or potential gradient, and proportionality constant of current density and applied electric field is known as conductivity. We can define conductivity as current density per unit of applied electric field intensity. Now in place of current density, if number of free charge carrier per unit volume is small n and drift velocity of those free electrons is v and charge of those electron is E, then current density is defined as NEV, and current density per unit of applied electric field conductivity can be written as, in place of drift velocity which is directly proportional to applied electric field intensity, we can write mobility times applied electric field, and this electric field intensity in numerator and denominator when cancel out, we can say conductivity of material become equal to Ne mu, where N is number charge density of mobile charge carrier or free electrons, E is charge and mu is mobility of free electrons, and mobility depends upon time between two successive collision or relaxation time. And in terms of relaxation time, conductivity can be written like this, where E is electronic charge and M is mass of electron, and this relation of conductivity Ne mu directly indicate that conductivity of metal depends upon number density of free electrons small n and mobility of electron in metal. In metallic conductors like silver, copper, aluminum, gold, we have a very high number of free charge carrier density. This small n is very high, and also mobility is also high. So the product of small n and mu results in higher value of conductivity. So these metals got high conductivity and they easily conduct electricity as well as heat. Whereas in materials like glass, wood, mica, paper, porcelain, PVC, they have a low number density of free charge carrier, and due to small value of this small n, conductivity of these material is small, so they won't conduct much both electricity as well as heat. So these glass, wood, mica, paper, porcelain, PVC, etc. are called as insulator. Whereas in some material, the density of free charge carrier, this small n is not that high as in metal or not that low as in insulator. This number density of free electron is of medium size, and these material have a conductivity less than conductor and more than insulator are called as semiconductor. And typical example of semiconductor which we will understand in this playlist are silicon, germanium. In solids, large number of atoms are brought together in a close proximity. In normal solid, in 1 centimeter cube volume, there is around 10^22 atoms. So they are very closely placed with each other, and various energy exchange interaction occurs between neighboring atoms. Now this will change energy level of orbital electron, especially of outer orbital, and will get altogether different energy level configuration in solid as information of energy bands. According to Pauli exclusive principle, no two electron of an atom has identical energy levels. And if we take an example of silicon, in gaseous atomic state, silicon got 2 electron in first orbit as 1s2. Then in second orbit, there are in all 8 electrons, 2 in s orbital and 6 in p orbital, but these are inner orbital electrons. In outermost orbit, we have 2 electron in s orbital and only 2 electron in p orbital. There exist 4 empty places in this 3p, and there are 10 places in 3d orbital. And as per Pauli exclusive principle, the discrete energy states of these electrons are shown by energy level in terms of discrete line in this energy diagram. Now in solid, when millions atoms interact with each other, these discrete energy levels of individual electron take number of energy levels equal to number of atoms. As a result, electron energy level splits into closely spaced several energy levels of negligible separation, and we call this group of energy level with negligible separation as energy band. And within an energy band, there are numerous energy level so closely spaced that we can say that energy are just nearly in continuum here. We can explain energy band diagram of silicon in terms of valence band, conduction band, and a gap in between the two valence band and conduction band as forbidden energy gap. If we consider an individual silicon atom in gaseous state, its energy level of inner orbital electron won't interact with neighboring atom, so we will not consider energy level conditions of inner orbital level in this band formation, but energy level of outer orbital electron interact with other neighboring atom, and we have 4 field energy levels, 2 in 3s and 2 in 3p as 4 lines here, 4 discrete lines here, and we have 4 vacant position of energy levels in this 3p, as 3p can occupy in all 6 electrons, but we have only 2 filled and 4 are vacant energy levels in an silicon atom. And when 2 such silicon atom are brought close to each other, no 2 electron of those 2 atom could have same energy level. So this 3s energy level 2 per atom become 4 for 2 atoms. Similarly, 2 levels of 3p become 4 energy levels, and per atom 4 empty space become 8 empty energy level states in this position of 2 silicon atom. And if we increase number of interacting atoms, the number of energy levels will become equal to number of atoms in interaction, and initially additional energy level occupy their position in between the gap of 2 energy levels, but when this gap get filled, energy levels will spread to both side of its mean value, and at one interaction, when interatomic spacing become small and more number of atom are in interaction, we'll find that 3s and 3p energy level split will merge together, and at actual crystal lattice spacing or interatomic spacing equivalent to A of actual silicon solid, we'll find that this merger of 3s and 3p again split into continuous energy level group and one continuous energy level group without any gap of lower energy values represent 4 electron per atom, which are field energy level of silicon solid, and this group of energy level is called as valence band. And after a energy level gap, we have another group of energy levels where an electron can be placed if excited and got energy more than this forbidden energy gap, and these are basically at 0 Kelvin condition or low energy condition, those energy levels which are 4 empty states per atom or unfilled vacant energy level at 0 Kelvin or lower temperature conditions. But if electron of valence band is given energy greater than this forbidden energy gap, it can be placed in conduction band, and in conduction band a position of electron in this band represent its free state, and those electrons can participate in electric conduction. So in silicon solid we have a group of continuous energy levels as valence band, then we have a gap of energy level where an electron can have energy values but won't have a separate position, and such electron has to be in valence band only, or they remain in bonding positions and won't participate in electric conduction. But if they got energy more than this forbidden energy gap and reach to conduction band, they can contribute in electric conduction as free electrons in our conduction model. Energy band diagram of semiconductor like silicon are rather complex. There exist several energy bands, and in between bands we have energy gaps, and below this third orbit we have energy band and gaps in first and second orbit also, and in between two energy band, energy gaps represent specific interval of energy levels where electron can have those energies but can't remain positioned in those energy levels, and we call those energy level interval as forbidden energy levels, and one such electron of forbidden energy level values has to remain in lower energy band. Now fortunately energy band diagram can be simplified, and only the top three energy bands, one fully filled energy level of highest energy values known as valence band, and one the first above that energy band of empty energy levels called as conduction band, and the third is the energy gap between valence band and conduction band. So these three, valence band, conduction band and forbidden gap, are of importance from the point of view of conductivity analysis. The valence band represent the electron of almost filled energy bands of highest energy, and conduction band is first partially filled band above this valence band after this forbidden gap. In silicon solid with interatomic spacing equivalent to 2.35 angstrom at 300 Kelvin temperature, the energy band gap is equivalent to 1.1 EV, and at this temperature condition of 300 Kelvin, few electrons, 1 electron out of 10 about 10 atom approximately, have good enough energy and that can surpass this energy band gap and can reach to conduction band, and such electron in conduction band can participate in electric conduction. In some material called insulator, the forbidden energy gap interval widely separate valence band and conduction band, or in semiconductor, the two valence band and conduction band may be close together with a small forbidden energy gap interval, and in another type of material called conductor, the two energy bands, valence band and conduction band, may overlap without an existence of forbidden gap. So we can say in material, forbidden energy gap interval may be large, small or in non-existence, and accordingly we can classify material as insulator with a large forbidden band gap interval, semiconductor as a small forbidden energy gap interval, or conductor with an overlapping and non-existence of forbidden energy band gap interval. The size or magnitude of forbidden energy gap interval depends on nature of material and it decides its conductivity. In normal state, the electron attached in covalent bond in semiconductor in crystal formation occupy the valence band or are called as bonded electron in atomic bondings, and they can't participate in electric current conduction. If these electrons of valence band acquire good enough energy to surpass this forbidden energy gap interval, which is 1.1 EV at 300 Kelvin in silicon crystal, then they can take position in conduction band, and such electron of conduction band are just like free electrons. They are not attached with respective remaining atom and can participate in electric current conduction. So for current conduction we need electron of valence band into conduction band, and that need energy more than that of forbidden energy gap interval. In metals like silver, copper, aluminum, gold or other metal and their alloy, there is no forbidden energy gap existence between valence band and conduction band, as the two valence band and conduction band overlaps. So even at room temperature condition, large number of electron of valence band are in conduction band and are available for current conduction. So without any additional energy, such metals, silver, copper, aluminum, gold or other metals and alloy, contain a large number of free electrons in conduction band position, and due to large number of free electrons in conduction band, they can conduct both heat and electricity very easily. For example, copper has around 8.5 into 10 to the power 28 free electrons per cubic meter, which is a very large number. Hence copper, like silver, aluminum, gold, is a very good conductor. Insulator has a energy band diagram as shown here, and there exists a large forbidden energy gap interval between valence band and conduction band, and ideally it is impossible for an electron of valence band to jump and surpass this forbidden energy gap interval to join conduction band position. Hence, due to absence or very small amount of electrons in conduction band, such material cannot conduct electric current or heat, and they are called insulator. The forbidden gap in most of insulator is very wide, more than 4 EV, and for diamond, one of the best example of insulator, this forbidden gap is about 8 EV. PVC, glass, wood, mica, paper, porcelain, all are example of insulating material, and such materials won't conduct in normal conditions and are used to stop flow of electric current as insulator at various positions, but they may conduct only at a very high temperature, and at elevated temperature condition some of valence band electron may reach to conduction band and start conducting leakage current, and this is called thermal breakdown of insulator. And to avoid that, one should not use these insulating material beyond their specified breakdown temperature limit. Similarly, such material may conduct when they are subjected to a very high electric potential that establish electric field strength more than the dielectric breakdown limit of insulator, and in that condition electron of valence band will reach to conduction band and material start conducting, and that shows the breakdown or damage of insulating material. So we never apply high electric potential to surpass dielectric breakdown strength of insulating material, or won't use such material beyond a temperature of specified safe limit. Semiconductors are in between insulator and conductor. They are neither like insulator having a forbidden gap of high energy level interval of beyond 4 EV, and nor they are conductor where valence band and conduction band have an overlapping, but in semiconductor we have a small forbidden energy gap interval of around 1 EV, and in semiconductor material at room temperature conditions the heat energy is sufficient to lift some electron of valence band to conduction band. So therefore at room temperature condition these semiconductor have a moderate amount of electric conductivity in between insulator and conductor. But if we consider the same semiconductor at absolute zero temperature or 0 Kelvin position or minus 270 degrees Celsius, then the highest energy possessed by electron is just midway of this forbidden gap called as Fermi energy level, and all electron being energy less than this level are positioned only in valence band and no electron is in conduction band. So at 0 Kelvin position in silicon, this valence band is completely filled as 4 electron per silicon atom, and this conduction band is completely empty as 0 electron per atom. And since there is no electron in conduction band, the semiconductor material at absolute zero temperature condition or 0 Kelvin or minus 273 degrees Celsius behaves like a perfect insulator. But if we increase temperature, the energy of valence band electrons will increase, the magnitude of forbidden gap also decreases, and more number of electrons may reach to conduction band, and in that condition increased temperature will increase conductivity of semiconductor material. We hope this beautiful learning video has explained conductivity model in material and also explained how energy bands are formed in solids, and you could now understand what is valence band, conduction band and forbidden energy band gap interval in solids. And as per this forbidden energy gap interval, we classify material as conductor, semiconductor and insulator. Our other learning video of the same playlist are equally useful to enhance your subject understanding and scoring ability in exams. You can use them in your study and share them with your friends. And if you need dedicated exam centric notes or online doubt clearing classes from our channel, do join our YouTube membership. Happy learning. Have a nice time. Thank you very much.